Hello and welcome to the Experimental Structural and Soil Dynamic Analysis webinar. This webinar was presented by ANCO Engineers in partnership with Testindo on the 29th of July 2020. Due to some technical difficulties, the first 5 minutes of the presentation recording was lost, and this introduction has been re-recorded. My name is Bose Norton. I'm the project engineer at ANCO Engineers, and I'm joined by Paul Ibanez, the chief engineer of ANCO Engineers, along with our representative in Indonesia, Zulfikri of Testindo. During this presentation, ANCO will be discussing our experience in building structural testing machinery, as well as giving examples of tests that can be performed for vibration and seismic analysis of various structures and components. All questions during the webinar are held till the end, and there is a lengthy question and answer period at the end of the presentation. The first topic we discuss is improving the seismic capacity of non-engineered structures. A non-engineered structure is typically a concrete framed building with masonry infill walls. These structures are typically built with little to no engineering oversight, and thus there is great concern for their seismic capacity. The best way to evaluate their seismic capacity would be a shake table test, which is pictured here on the left. This is a preliminary concept for a large 6 degree of freedom shake table that would be used to test a full-scale 2-story non-engineered structure in order to determine its earthquake capacity, and ultimately to evaluate any increase to that capacity using a variety of inexpensive structural upgrades. We will now resume the recording of the webinar with Paul Ibanez discussing this proposed test in further detail.
A large earthquake, some cities are estimating that millions of people could die due to collapse of these structures in an earthquake. And so researchers at universities in these countries are trying to put together a group to analyze these structures by placing them on a large shake table. The shake table concept shown in the slide is a biaxial table. That means it moves in both X and Y directions, horizontal directions. And the table concept, this table would be 4.5 meters by 4.5 meters in size. And you could put a full-scale 2-story reinforced concrete structure up to 6 meters high on the table. This is similar to what is used in many of these countries. The first phase of the experiment would be to put different designs of these tables, of these structures on the table and expose it to different levels of earthquakes. The goal will be to understand at what level of earthquake motion these structures begin to have damage or significant damage and then collapse. So that will be the first step of the study, and it will help to decide how much is the risk. The second part of the study will be that they will begin to put the structures on the table that have had relatively inexpensive and economical improvements, additional steel braces, better tying in of the beams and columns, and so forth. And therefore, they will try to find ways both to build these better from the beginning, and also, if they are already built, how to retrofit them to give them larger earthquake capabilities. So we are hoping that these studies move forward, and the table is used in the next 2 years, and that this would be of great benefit in trying to reduce the casualties in large earthquakes in many countries of this world. So this is an example of how a shake table can be used to solve some very difficult problems. Because the failure of these structures are nonlinear, it is very hard to analyze them analytically, and this is one reason why one would use a shake table to do this study.
All right. Next, let's talk about another example using a shake table. Their shake table evaluation of structures doesn't have to be these non-engineered structures. It could also include historical structures, such as the one pictured on the left. This is a model of the Hagia Sophia Museum at the Bogazici University in Istanbul, Turkey. It doesn't have to be a historical structure either. Modern buildings need earthquake testing on shake tables, such as testing the facades on modern high-rises.
Right. This shake table at the Bogazici University in Istanbul is 3 meter by 3 meter, and it can handle payloads, test models, up to 7 or 8 tons. And in one experiment that is shown in the photograph, they decided to investigate the seismic capacity of the Hagia Sophia museum in Istanbul. This museum originally was a cathedral, and then a mosque, then a museum, and now it has returned to being a mosque. But in any case, it has been in existence for about 1,400 years and has survived many earthquakes. And so the researchers were very interested to understand how it has been able to survive earthquakes and how the structure works in the case of this historical structure. They found out many interesting things indicating why it has significant seismic capability, even though it was designed 1,400 years ago. This same shake table is also used to test modern structures in Istanbul. Istanbul is a growing city with many high-rise buildings, and high-rise buildings have either glass or stone facades, covers on the outside of the building. And there was a great concern that these glass outsides or stone outsides would fail in an earthquake and fall to the ground and cause great casualties in an earthquake. And so on this table, they have also assembled many frames with full-size samples of glass and stone facade of the high-rise buildings in Istanbul and exposed it to very high earthquakes. This table is able to achieve a peak acceleration of about 2G. And so by using this, they have been able to prove and improve the attachment methods of facades to the high-rise buildings in Istanbul, again leading to greater seismic safety. So this is another example of how shake tables can be used to solve difficult problems that are analytically difficult to analyze.
Some other types of tests that are often performed using shake tables are related to soil studies. Soil liquefaction and structure interaction can be studied on a shake table using soil boxes and laminar boxes. Pictured here on the right is a rigid wall soil box that ANCO built, and on the left is a laminar box, which means slightly flexible walls that ANCO designed, both of these for use in shake table testing of soil interactions.
Right. Very often people will analyze foundations in these soil boxes. The shake table will shake the soil box. The soil box will have soil in it, but with a model of a foundation. This could be a machine foundation, for example, a turbine, or any other kind of structure. And it is possible to measure how the structure responds inside the soil, inside the box, and therefore do a complex soil structure interaction analysis. The reason there are two boxes is that the less expensive boxes are the rigid wall boxes, in which there is just a steel or aluminum box where the soil is placed. But this can introduce some inaccuracies because the soil box is not infinite. When you have a foundation, there's a great amount of soil around it. And so when the foundation radiates energy, the energy travels away and never comes back to the foundation. But in the soil box, the energy can bounce off the walls of the soil box and come back and affect the answer. And so that's why in a more expensive setup and experiment, people will use these laminar boxes. These are boxes also made of metal, but with many layers, anywhere from 5 to 20 layers, separated by rubber, so that the walls of the box, in fact, are flexible and they tend to absorb and not reflect the waves in the soil back to the structure. So there are some very interesting ways of getting better answers. And this is an example, again, of using a shake table to solve soil structure problems in some creative ways.
There are many additional applications for shake tables listed here, just some of the many possibilities, such as evaluating the performance of piping systems, cable trays, raceways, ducting, partitions, suspended ceilings, lighting fixtures, that sort of thing, or other types of scale models, testing of large structures, such as multi-story buildings, which we've already discussed, but also bridges, dams, machine foundations, and offshore oil platforms. Or you can test the equipment that goes into a building, such as the mechanical, electrical, and communication equipment.
Right, just again, it would take too long to describe tests on all these structures. But for example, a very important testing program that is going on in the United States and other countries is the ability of mechanical equipment in critical buildings to survive an earthquake. People are very concerned about the equipment inside police stations, fire stations, and hospitals, because after a large earthquake, it is very important that the services of the police, the fire department, and doctors continue. And so it is not acceptable that these buildings will stay up, but the equipment inside would fail. And so there are many tests on shake tables now to prove that critical equipment, such as communication equipment, such as computers for medical analysis, X-ray machines, oxygen systems, and so forth, continue to operate. Because after an earthquake, that's when these critical facilities have the greatest need to continue to operate. And so currently in the United States and in other countries, there is much testing of mechanical equipment that goes into critical structures. Another example of the use of shake tables to solve difficult dynamic problems.
We've given a lot of examples of the types of tests you can do on a shake table, and here's a example of an actual university research shake table that was built by ANCO and installed at the Gajah Mada University in Yogyakarta, Indonesia. This was delivered to Professor Suhendro and Professor Henriques. I know some of the participants in this meeting may be very familiar with this table as they've used it themselves. But for those not familiar, this is a typical ANCO designed for a one-axis shake table, meaning it moves in the horizontal direction only one direction. The stroke is plus or minus 10 centimeters. It is driven with a servo hydraulic actuator. And the table surface is 1.5 meters square and can provide a 1.5 G capacity with a 3-ton payload on the table. So this is a table I'm particularly proud of, as I traveled to Indonesia in 2016 to install this table. Professor Suhendro, pictured there next to me, was a very gracious host, and the Borobudur temple I got to see was probably the most amazing place I've ever been. So needless to say, I had an amazing time in Indonesia and truly hope to have the opportunity to return one day and install some more equipment. But enough about shake tables. Let's talk about some other types of testing, such as field vibration tests performed on actual full-size structures. Pictured here on the left is a eccentric mass vibrator. These machines have a pair of rotating masses that can produce a vertical or horizontal force. This allows you to excite a structure and determine its vibration characteristics by measuring at many points on the structure. Those structures could be anything from a 1 to 50 story tall office building, bridges, dams, oil platforms, turbine foundations, and other power plant structures. This particular vibrator, the Mark 139, was recently built for testing railway bridges in Jakarta.
The reason we would use vibrators instead of shake tables is that sometimes the object you want to analyze is too large to put on a shake table, such as a large bridge or a large building. And in that case, you can still investigate the dynamic properties of structures by putting these vibrators on the structure. They are controlled by a precision speed motor that can change the frequency of the rotation of the weights. And as the weights rotate, they introduce a sinusoidal force into the structure. The vibrator that is shown can produce a force up to about 100 kilonewtons, 10 tons. And you can put this on a large building, a large dam, a large bridge, and get significant amplitudes. Typical testing amplitudes, even on large structures, is you can excite the structure as much as 2 or 3% G, acceleration of gravity. And as you sweep the frequency from low frequency to high frequency, you will have accelerometers on the structure, and that you will analyze the sinusoidal response, and you can identify the resonant frequencies of the structure. You can identify their mode shapes, and you can identify their structural damping. Structural damping in particular is very difficult to predict theoretically, and so it is good to do tests on structures to check this. The other reason why this is a useful thing is that when you measure the resonant frequencies of a structure, you can compare it to a finite element analysis model, and you can see how accurate the model is and how it can be improved. And as I mentioned, you can also measure actual damping in the structure and use this in the earthquake analysis of the structures. The other thing you can also do is periodically test the structure, say every 2 or 3 years, and see if the resonant frequencies and the mode shapes are changing, which might indicate that there is degradation or reduction in strength of the structure. So by doing this, it is possible to get some very good information, to confirm models, and to understand the true dynamics of complex structures, again, even if they are embedded in soil. So these eccentric mass vibrators are used in many applications.
Another application that is performed in the lab rather than the field would be static and dynamic load frame tests. These load frames are used to react single or multiple hydraulic actuators onto a test item. Shown here is a frame that ANCO recently built for the Hashemite University in Amman, Jordan. And this particular model has a 1,000 kilonewton capacity and is used for testing concrete structural beams and panels.
This is something which might be much more familiar to you than shake tables or eccentric mass vibrators. But they are also a useful way of solving some problems, such as the failure of panels and beams, by testing them statically or dynamically with hydraulic actuators attached to these kinds of reaction frames. In particular, I am thinking of one project that was done at Drexel University in the United States, where it was a desire to accurately model the vertical and horizontal capacity of a masonry wall. And so they put a masonry wall in one of these frames with 2 vertical actuators and 1 horizontal actuator. The horizontal actuator would shear the wall to simulate earthquake excitation. The vertical actuators would press down on the wall to simulate the actual load of the full structure on the wall. And by doing this, they were able to develop models of masonry walls that more accurately predict the kind of earthquake response you get in such structures. So these kinds of laboratory tests with servohydraulic actuators under computer control are another useful way to do structural dynamic analysis, especially when things are going nonlinear because they are failing.
Another very different application is using geocentrifuges for scaled model testing. Pictured here is a 450 G-ton centrifuge that ANCO worked on in Tianjin, China. The basket hanging on the end was something ANCO built to contain a shake table, which was used for velocity scale testing. And there's a lot of issues that need to be considered when dealing with scaled model testing.
Right. You know, there is always the problem that sometimes structures are too big or too expensive to do testing. And so, especially in soil dynamic studies, people would like to do scale model testing of structures in soil. And sometimes the scale factor is a factor of 100 or more. And so it's necessary to do analysis and understand how the performance of a model 100 times smaller than the real structure compares to the real structure. And so the mathematical analysis is shown there under a concept called velocity scaling. And under this case, the size of the structure is reduced by 100, but the resulting accelerations during an earthquake have to be increased by 100. The displacement are decreased by 100, and the mass of the structure changes by actually 100 to the third power. But the very interesting thing is that if you want to accurately represent the soil, then Earth gravity has to increase by 100. You can imagine that if you have a small model and it's in a box with soil, say perhaps half a meter high, there is not the gravitational compaction of this soil. And the containment pressure on soil is very important to correctly represent its actual stiffness and strength properties. So the only way a scale model can be truly accurate is if you scale Earth's gravity, which means you have to do your test at a high acceleration, like 100 Gs, static. And where do you find a place? You know, you cannot take your model to a large planet like Jupiter, where the gravity is much higher. So instead, you put it inside of a centrifuge. And that is what's shown here. And there are many of these centrifuges around the world and are used very much for looking at problems of structures in soil, especially in water hydrology, offshore oil structures. And so if you are trying to analyze things such as piles, retaining walls, dams, and similar structures, you can do this scale model testing accurately if you do it inside of a centrifuge. And in this case of the centrifuge in China, we were able to put a high acceleration shake table inside the centrifuge. So the shake table would do its earthquake testing at the same time the model and the soil were being compressed by 100 G acceleration. And in this way, you get accurate answers and behavior of the soil. And this is therefore a way of handling very difficult nonlinear soil dynamics. Some of these centrifuges, as shown there, are very large. When they say 450 G ton, it means you can have a 3-ton test item and test it up to 150 Gs. But you can also do tests with smaller centrifuges, and this is shown on the next slide.
As Paul said, here's one example of a kind of test that ANCO saw performed at the Sheffield University in United Kingdom. They were testing pile strength in a scaled model. This particular test used a scale factor of 100 with an acceleration of 100, and there was a scale model pile embedded in sand, and then it used a pneumatic actuator to push over this pile as it was being accelerated to 100 Gs.
Yeah, by doing this test, they were able to determine how much force was required to fail the model pile, and then they could scale that up to how much force it would be required to fail the full-scale pile. And this is a very nonlinear phenomena, and therefore it would be very hard to analyze. But in this manner, they were able to get accurate data and improve the models of piles in soil that are both dry or saturated, like underwater. And similar tests are done to look at the failure of embankments, the failure of walls, and so forth. They have either shake tables in the centrifuges to excite them like an earthquake, or they have pneumatic actuators to simulate wave action, or just to simulate the forces of the embankment on a wall. And in this manner, many universities can analyze these complex soil structure problems and improve their computer models and get better and more safe and economical structures.
Well, that concludes our presentation. That was a lot of examples, and we only very briefly got into each one. But the rest of our time here, we'd like to answer all of your questions. I see we've already received several questions. If you have any more at this time, please continue to submit them. Let's see. Zulfikri, would you like to translate some of these questions for us?
Hello, I think there is a question in English in the question and answer form.
Okay, well, I'll start by answering the questions in English, as that's my preferred language, but then we'll move on to translating next. The first question is, shake table and wind tunnel test, is the approach the same? What correlation ratio between the real and the test?
Well, again, when you do wind tunnel testing, by and large, you cannot test a full-size structure. So just like the geocentrifuge, there will be certain scaling laws that apply, so that the density of the gas, the velocity of the gas, and the response of the structure have to be analyzed with these scaling laws. Now, I understand the scaling laws in geocentrifuge very much. I am not fully familiar with the scaling laws in a wind tunnel, although I know similar laws apply. If you're interested, you can send us an email, and I will try to find a little bit more information about what the scaling laws are in wind tunnels. You know, it is a similar thing, but a slightly different technology.
We should also say that if you have a question in the future that you don't have time to ask here, you're more than welcome to reach out to us through our website or by email or through Zulfikri, and we'll be happy to answer your questions at any time. But the next question we're going to be answering here is the correct term shake table or shaking table?
Okay, I think people use both, okay? We like to use shake table, but a lot of people say shaking table, and some people also say shaker table. So you can choose what you prefer. People will understand.
All right, one more question in English, and then we can answer some of the ones in Indonesian. Is that possible to physical modeling the slope stability so we can compare with software output? How to make sure the size of the model, dimension and weight is accurate? What is the method for pushover earthquake that is possible for modeling? How do you consider aging material degradation, such as corrosion, for existing structures?
Okay, well, embankment studies are very popular to do in a geocentrifuge. Because, you know, again, you can do the scaling. And for example, if you're looking at an embankment against a wall, and you're worried about the wall being forced over by the soil pressure, you can do this in a geocentrifuge. There are various techniques for doing this. Again, you can temporarily support the wall with a pneumatic actuator, and then you can place the soil in place, and then you can release the pneumatic actuator and see if the wall is stable or whether the wall collapses under the pressure of the embankment. Similarly, if you are concerned with the stability of an embankment with an earthquake, you can, in the geocentrifuge, you can, again, create the embankment and put it on a shake table, and then shake it and see if the embankment soil collapses or not. In such tests, very often, people will use video cameras, high-speed video cameras, to look at the sample in order to be able to track what happens, and if the embankment fails, how it fails, what are its displacements. And so, this can be done. You do have to be, very careful in how you use the soil and how you place it. First of all, you should use soil that is the same as the soil you're going to use on the real structure. You also have to be careful on how you lay down the soil. And many of these geocentrifuges will have a special soil robot that will let the soil down into position in a very controlled way by raining it down while the centrifuge is rotating. And that way you get the most accurate results. The issue of degradation over time is somewhat more complex, and that is something I cannot comment on very much, but it would be interesting to see, because in the centrifuge, you generally don't, wait for many years for something to happen. You're doing the test over a few days. So I'm not sure how you would handle the degradation aspects, but that is something that we could look up and try to get you some more information. We do work with various professors around the world who do this, and again, if you send me your contact information, I will get you some answers back on the degradation issue.
That was a lot of questions all at once. So thanks for that response, Paul. If we didn't quite answer your question, feel free to ask again. But let's move on to this next question. Is what is the biggest size of shake table available in the world, and where is it?
The largest shake table in the world is in Japan, and let's see, it's called the military something shake table, but it is about 30 meters by 30 meters in size, and it can support a very large structure weighing several hundred tons. So that's the largest in Japan. The largest in the United States is about 5 by 5 meters in size, and it can support about 50 tons. And there are other shake tables around the world. Typical large shake tables, in most universities are about 3 meter by 3 meter, although some universities have 6 meter by 6 meter. So that gives you, just some idea of what can be done. Many universities also have smaller tables for educational purposes, and ANCO, for example, makes shake tables anywhere from ½ meter by ½ meter up to 6 meter by 6 meter.
The next question is somewhat related to that. I believe someone is asking about the parameters of a typical shake table test and how the validity of those parameters is compared to real cases.
Okay, well, again, different tables have different capabilities, not only size, but typical shake tables are able to produce accelerations on the order of 1/2 G to about 5 Gs. These are typical earthquake shake tables. They also typically have velocities on the order of peak velocities of 1 to 2 meters per second. And the peak displacements are typically between 20 and 200 centimeters peak to peak motion. The other thing about shake tables is how many axes. Many shake tables are just one axis, say horizontal or vertical. But there are tables which have 2 axes, like we talked about earlier. There are tables with 3 axes. And also for some special applications like ship motion, there are tables with 6 axes. You know, the larger the table, the more axes, the more capable, but also more expensive the tables are. So these tables can be used to reproduce actual earthquake motions or earthquake motions specified by government regulators, saying that equipment, say, in a hospital must survive this size earthquake. And the tables are very good in reproducing the motions of real earthquakes. And so it looks very much like an earthquake, and if you stand on the table, it feels very much like an earthquake. And these tables can produce their own artificial type earthquakes, but also if you have measured earthquake motions with a seismograph, you can enter that into the control computer, and the table can reproduce the actual motion of the particular earthquake you're interested in. The one thing that shake tables generally cannot do is reproduce very low frequency motion. You know, real earthquakes have motion anywhere from 1/10 of a hertz up to 30 or 40 hertz. Now, most mechanical equipment and most structures have resonant frequencies above 1 hertz. So most shake tables can do a good job of reproducing earthquakes from about 1 to 30 hertz. Even though, you know, large earthquake motions of several meters can occur, but that's at very low frequency, and in general, it does not affect buildings or mechanical equipment. And so most shake tables do not do a very good job of reproducing earthquakes below about 1 hertz. But you know, there have been some shake tables made which have longer stroke, up to plus or minus 1 meter or 2 meters, and they're used for testing very low frequency type of equipment or water motion in water tanks. So many different capabilities in a table and specifications.
And hello, Paul. Before
Yes.
starting next question, Mr. Suhendro would like to have a question to you, but I would like to introduce him first to all audience.
Okay.
Bapak-bapak, ibu-ibu, saya perkenalkan salah satu peserta webinar kita, Profesor Bambang Suhendro dari Lab Struktur UGM. Beliau salah satu yang telah memakai produk sektable dari ANCO. Pak Bambang, silakan Pak. Please, Mr. Bambang Suhendro, to directly ask the question.
Okay.
Professor Suhendro, could you raise your hand and I'll add you as a panelist?
Pak Bambang silakan.
One moment, please. All right, let's see. Okay, go ahead and ask your question.
Yes, okay. Hello, Paul, Boas.
Hello,
Nice
Professor
to meet
Suhendro.
you again. Yeah,
Hello.
welcome virtually to Indonesia.
Thank you.
Okay, I think it is midnight in Colorado, I believe.
No, it is about 10:30 in the evening.
Oh, 10:30. Okay, thank you. I have two questions for you. The first one is related to our shaking table in our lab. It is one axis or one dimension, right? The excitation of the earthquake. Is it possible to upgrade the table to two-dimensional? This is the first question. And the second one is related to the tune mesh damper. In Indonesia, we have several problems related to the vibration during construction. During the, for example, bridge construction, long span bridges, we need to stabilize the end of our hang construction at the time stage with the tune mesh damper, both for wind and earthquake forces. Yeah, those two questions is enough, I think. Thank you very much, Paul and Boas.
Okay, well, to answer the first question, the answer is yes. The table can be upgraded to more axes. The easiest upgrade is to add another horizontal axis. Right now, your shake table can move in the X direction. It would be possible to upgrade it to move independently in both the X and Y direction. That would be the easier one. A more complicated upgrade would be to move in the X and Z direction. It is possible, but it would be somewhat more expensive. So yes, it can be done. Send us some specifications and we can explain that in greater detail. In terms of tuned mass dampers, these are very interesting ways of reducing the vibration of structures. Basically, what you do is you add another resonator to the structure, and this resonator has a lot of damping by using, say, servohydraulic actuators. And what this does is it takes one resonance of the original structure, which may have low damping, and changes it into two resonances of the combined structure and tune mass damper, which has higher damping. So, for example, if you have a floor of a large building which is vibrating too much, it could be because it has a vertical resonance and only 1% damping. But by putting a tuned mass damper under the floor, you can change it to have two resonances, which sounds bad, but these two resonances can have damping of 5%. And two resonances with 5% damping is actually a much better structure, less vibration, than one resonance with 1% damping. And so this has been used for building floors. It has been used for entire buildings vibrating in the wind. It is even used in some machinery, like machine tools, to reduce the vibration in the machine tool. And so, yeah, tune mass dampers are very interesting and very useful and relatively inexpensive. They can solve some problems. They've been used, for example, in bridges also.
All right, well, thank you for your question, Professor Suhendro. We've got about 20 minutes left for answering questions, and almost 20 questions left to go, so we'll do our best to get through them as quickly as possible. The first one should be easy. Paul, can you just briefly go over again what a 450 G-ton centrifuge is referring to?
All right. Geocentrifuges are rated by referring to G tons. And what that means is you take the maximum mass of the test item you can put in it in tons and multiply it to the maximum acceleration that the centrifuge can impart in that test item. So for example, if you had a 1 ton test item, the model, 1 ton, and you could expose it to 200 Gs, that would be 200 times 1 is a 200 G-ton centrifuge. So small centrifuges for education and simple tests are rated, you know, something on the order of 10 G-tons, perhaps 30 G-tons. Very large centrifuges are rated closer to 500 G-tons or even a little more. So for example, if you have a 500 G-ton centrifuge, it means you could put a 5-ton test items and excite it to 100 Gs. Or you could put a 2.5-ton test item and excite it to 200 Gs. So that's why it's a good measure of the basic capability. I think the largest geocentrifuges in the world can go up to about 650 G-tons.
There's another question about that. What is the biggest centrifuge and where is it?
Okay. To my knowledge, the largest centrifuge in the world is at a government laboratory in the United States called the Army Corps of Engineers. And that is a centrifuge of about 650 G-tons. And they use it very much for studying embankments, because the Army Corps of Engineers in the United States is responsible for the large embankments and the large rivers in the United States. So they like to model what they do in making dikes, walls, embankments of all sorts. And they like to use the geocentrifuge to check their work.
All right. The next question is actually a 4-parter, all related to the Mark 139 eccentric mass vibrator. I'm going to go ahead and ask them all, and Paul can answer them, I think, pretty quick. What's the total weight of the Mark 139, and can it be mobilized in a double car cabin? What's the maximum weight of the eccentric masses? Is the mass, weight, and speed, can they be changed so the vibration frequency can be adjusted to detect its bridge structural resonance? And is this equipment available in Indonesia? What institution has it? And yeah, we mentioned it was being used for railway bridges.
Okay. We have many of these vibrators. The Mark 139 is about a medium-sized vibrator. And its total mass is about 500 kilograms. But it can be broken up into smaller parts less than 100 kilograms. So it can be transported in a small truck. You know, it's possible to do that. It's also possible to transport it in a small aeroplane also. The masses can be changed. You can subtract or add the masses so that you can go to different frequencies and get different forces. So it's fairly easy to change the masses in order to study an entire range of frequencies. This particular vibrator operates well between 1 hertz and 30 hertz. The variable speed drive that drives it is very accurate. It can control the frequency of the vibrator to about 0.1% over the 1 to 30 hertz range. And so you can take very fine frequency steps, and it's all controlled by a computer, which also analyzes the data from the accelerometers and does a sweep. So you can identify the resonant frequencies of a bridge or any other structure, and you can identify a resonant frequency even if it's only 1% damped. In terms of vibrators, we, in particular at ANCO, we have sold one vibrator to a company in Indonesia called RISEN, R-I-S-E-N, and we are in the process of building a vibrator for a second company. There may be other vibrators in Indonesia, but I do not know about them.
Okay, Paul, could you please explain the servo actuator concept that we use in our shake tables?
Okay, servo hydraulic actuators, they're basically a piston, a double-ended piston. And there is a very high performance servo valve attached to each side of the piston. And this servo valve is under computer control. This servo valve operates, can change the direction of the oil into the actuator about 200 times a second. It can reverse it. And so by reversing the oil flow in the actuator, you can make the actuator move in and out as you wish under computer control. The basic way it works is that attached to the actuator is a displacement transducer. And there is a servo controller which looks at the commands from the computer as to what kind of motion you want: sinusoid, random, earthquakes. And so the servo controller looks at that signal and then compares looks at the actual position of the actuator from the displacement transducer, and it instructs the valve to change the oil from the left side to the right side of the piston in order to get the same displacement. And it can do that, very quickly. And so these shake tables can easily follow a random time history, at least to 30 or 40 hertz. And in some special shake tables, it can follow it to 100 hertz, even more. So it is possible to get the actuator to move very accurately over a wide frequency range. And then you attach the actuator to the table, and the table moves in the same way. So you need the actuator, you need the high performance servo valve, you need the servo controller, and also you need a hydraulic power supply. On smaller shake tables, the hydraulic power supply only has to be perhaps 50 liters per minute. On very large shake tables, you may need a hydraulic power supply that is able to deliver 5,000 liters per minute. So it all depends on the size and performance of the shake table. I hope that's clear enough basically on how it operates.
Could you tell us how to measure the response of a structure while or after doing a shake table test?
All right. The most common way to measure the response of the structure is with accelerometers. There are several different kinds of accelerometers, but basically they're just very small mechanical parts, about 1 or 2 centimeters in size, and you put them on the structure and you connect them with a cable to a data acquisition system, and they produce a voltage proportional to the acceleration of the structure. So you can know how much the structure is vibrating in acceleration. You can double integrate that signal and then find out how much the displacement is. It's also possible to directly put a displacement transducer on the building and therefore directly measure displacement. It's also possible to put strain gauges on the structure and so measure the strain in the structure. There are also other techniques where you can take a video of the structure vibrating, and then you can analyze the video at many points in the structure and determine what the displacement is. So, you know, there are many options for measuring the motion on the table.
Could you explain how you would, how a shake table could be used to model a dam against earthquake events?
Well, there are, okay, obviously, you know, a shake table has a limited size. You know, dams are usually very large, 100 meters, perhaps more, but you can always put a model on the shake table. And if you are not concerned with soil structure interaction, for example, if it was a dam in rock where there is not much soil structure interaction, then you don't have to worry about doing it in a geocentrifuge. You can basically shake the model of the dam with the shake table, but it has to be a shake table that has much higher frequency capability, because the scaling factors will mean that the model will have higher resonant frequencies than the real dam. But it is possible to do that. You can shake the model, and then you can translate that into what the real size dam would do. If, however, you know, the dam is very much affected by the soil that it is in, then you either have to use a geocentrifuge shake table, or you can put the model of the dam on a shake table and just be at 1G Earth gravity. And then you will get a certain response, but it will not be accurate, but it will give you a case that you can check your computer program with. And then what you do is you use the table, the 1G test on a table to create data that you will check your computer program with. And then that computer program can say, okay, now that I know I am accurate, I can predict what the full-size dam would do. So there's you know, different approaches that can be done, you know, with different accuracies.
Slightly related question, could you tell us how to scale a structure that will be tested on a shake table? What is the experimental method and its relationship to geometry scale, the strength scale, etc.?
Well, the slide, our third from the last slide shows what some of these scaling parameters are. Again, there are different kinds of scaling, but the most popular one is this velocity scaling. And you know, as it says in the slide, you have a scaling factor S. You know, so if S is 100, it means that the model is 100 times smaller than the real object. Okay, so in this application, you build your model 100 times smaller. Okay, but because of the scaling laws, time changes by a factor of 100 if you use the same material as the real structure. So the resonant frequencies of the model structure will be 100 times larger than the real structure. Then if you want to excite it on the shake table, in order to get the same strain in the structure, you have to shake it 100 times the acceleration. And so if you have a very, if you have a small model, you're going to have a shake table that can go to much higher frequencies than normal, perhaps 300 hertz. You also need a shake table that can go to much higher acceleration, perhaps 50 Gs. And then you can excite the model and get the same strain in the model as the real structure, so that if that strain is going to break the real structure, you will also break the model structure. So you can do it, but depending on the scale models that you do, you need a special shake table. It's somewhat easier, for example, if you were testing a model of a building and you could put a building on the shake table that is, say, 1/4 the size of the real one, then things are a little easier, because it means that its resonant frequencies will be only 4 times higher, and that is easier to do. And you only need 4 times the acceleration. By that I mean, on a building with a scale factor of 4, let's say your earthquake is 0.25 G. Well, then the model, you have to accelerate at 1 G, and then you will get the same strain and breaking of the model as you would with the real structure. Again, this is a large subject. Send us an email. We can send you more information about it.
All right, Paul, what would you do if you wanted to measure the characteristics of an aircraft engine and its propellers? Particularly, they want to find out the natural frequency.
Oh boy. Well, fortunately with an aircraft engine, you can probably use the full-size aircraft engine. And what you can do is you can put accelerometers on the aircraft engine and operate the engine and perhaps sweep it through different frequencies or different rotation rates. And then you can identify resonant frequencies. The other thing you could do is you could use impact hammer testing, where you have the accelerometers on the various parts of the engine, and you strike, you use a small hammer with a plastic head, and you strike the various parts of the engine and measure the resonant, the vibration, which will tell you the resonant frequencies. One place which is difficult, if you are interested, for example, in looking at the resonant frequency of the rotating blades, obviously you can put an accelerometer on, but you cannot have a cable going to your data acquisition system. And so they do have accelerometers now which are battery operated, and they communicate with radio waves, with the digital signals to the data acquisition system. So the accelerometer can be rotating with the blade, and you can still measure its signal without cables. So yes, it is possible to do this with a variety of techniques. Again, if this is your interest, send us more information. We will send you more specific ideas.
All right, let's talk a little more about the soil boxes. How would you fill it so it resembles the conditions in the field, especially regarding soil, water, and soil layers?
Okay, you do have to be careful. You cannot just throw the soil in because the way it settles, it can be very different than in the field. And the best way to do it is to have one of these soil robots, which is basically just a box with the soil in it, with holes in it, and you slowly let the soil fall down into the soil box. And that is like the most natural deposition and gives the best results. If there are soil layers, different kinds of soil, you can do that. You can get the different kinds of soil and put it down in layers. Similarly, if the soil is saturated with water, you can add the water, doing it carefully, but you can add the water and pretty closely simulate what the real structure is like, the real soil and structure connection is like. You do have to be careful, because if you are not careful how you construct the soil, you can get errors in your analysis.
All right. Several questions about offshore platforms. The first one says, in the offshore Northwest Java Sea, there are 4 platforms, subsidence uniformly. How can we anticipate that something like the, excuse me, sorry, I should have read this question ahead of time. Let's see, there's a lot of questions about offshore oil platforms. Paul, can you describe some of your experience testing those?
Sure. I can talk about 2 kinds of tests, one of which I have done and one of which I have read about. There is great concern about subsidence of offshore oil platforms because the soil under the water is very nonlinear and very difficult to model. And so this is work has been done in geocentrifuges, where again, you get some of the soil from underneath, and you actually create a box with the soil and the water, and then you bring over your offshore platform that is perhaps floating, and then you let it drop into the soil. So you can simulate how the platform is moved into place and then dropped into the soil. And this gives fairly accurate answers as to whether the platform will be stable in the soil. You can also, in case you don't drop the structure in, but are basically constructing it in place, what you can do again is, in a geocentrifuge, put the constructed tower in the soil, and then you can use either a wave generator or a pneumatic actuator to simulate the effect of waves. So you can push in a sinusoidal manner on the structure, or you can have actual water waves hitting the structure, and you can see if it is stable. Does it tilt over? Does it sink more? You can do this all in a geocentrifuge. So, that is a good way. If you have stability concerns with offshore oil platforms, geocentrifuges are very helpful. The other way we have investigated offshore oil platforms is we can put an eccentric mass vibrator on the platform and do a vibration test to determine its resonant frequencies and its damping. So again, this can be used to confirm the finite element model. Is it accurate, or does it need to be modified? And so that's a good way of predicting how it will respond to waves. You can get a validated finite element model, so you are more confident that it is predicting the right response to waves, the right fatigue into the joints of the structure. And so using this experimental information can greatly assist in the accuracy of these calculations. There has also been some work done to monitor the response of offshore platforms to actual wave action, and then calculate back how much fatigue has gone into the structure. And so you could, for example, have a system on an offshore platform, and it could report let's say during a winter storm, how many fatigue cycles have gone into the elements of the structure, and therefore, do you have a problem? Do you have to do underwater inspection, and so forth? So, you know, there are ways that these experimental techniques can help with offshore oil platforms.
All right, we've only got less than 10 minutes before we're scheduled to end this session, but we'll try to answer a few more of the quicker questions if we can. Paul, can you briefly say what percentage of accuracy is generated by the shaking table against field conditions?
Okay. I guess there's several ways to answer that question. You know, if you are trying to say, I am shaking a piece of equipment, and how realistic is that to field conditions? In general, it's pretty good. The only place you can get into trouble is on the anchorage. You have to closely simulate the anchorage of the field installation on the shake table. And sometimes it's easy to do, and sometimes it's more difficult. So for example, if the equipment is mounted in a concrete floor in the field, it may be a good idea to put a concrete floor on the shake table and anchor it in the same way. So, you know, you have to be careful to get the anchorage conditions right. And if you do that, you are pretty accurate. You know, I would say, this is a very broad brush number, you know, you can predict the experience of the equipment, you know, to within 20 or 30% of what will happen in the real earthquake. You know, the same thing is if on a shake table or with a shaker, you are trying to find the resonant frequencies of a structure, you will often find that, you know, the experimental value differs from the finite element value by anywhere from, you know, 10 to 30%. If you get it more accurate than 10%, you're doing a very good finite element model. But you know, this is the kind of differences you can see between a shake table and a structure in the field. If you're looking at this modeling issue, testing models, again, if you're careful with the model scaling, construction, and anchorage, you can get good results. You can, again, be within 30% of what really would happen in the field.
Okay, I think we've got a few more quick ones here. Can the results of shake table tests be used in construction to overrule the practical code?
Well, that will depend a lot on the code writers. It depends if the if the government or whoever is writing the codes, the industry groups, if they can agree on that, it's okay. If they don't agree with it, then it's not okay. The place that, sometimes it can help, for example, sometimes codes will say, you must assume that the damping in this building is 3%. And if you do the analysis, perhaps that is difficult to make the building work. But on the other hand, if you can go and you can measure the damping and show that it's 5%, then you can use that in analysis and say, look, in my structure, I've shown that it's 5%. And if I use 5%, the building is okay. Whereas if I use 3%, it may not be okay. And so in that sense, it can, in a sense, not override, but complement local codes.
All right, I want to ask this last question from my friend Mr. Yachty at UGM. That's the example one-axis shake table we gave. He wants to know how a system with two multiple shake tables would operate. How would the computer control of a dual shake table system work, and could a single axis shake table like the one at UGM be upgraded or modified to work in tandem with another shake table?
Yes, ANCO and other people have created multiple shake tables that can be synchronized or move in different ways. So, like for example, in testing piping systems or testing bridge models, it's a way of making two small tables act like a big table. So you can have two small tables separated by many meters, but the computer can synchronize them to move together or even to move differently to look at differential motion. And so, yes, tables can be upgraded. You can have multiple tables. ANCO once built a system with 4 synchronized tables for testing piping systems. Other people, have done similar things. So yes, synchronized tables, can be built, and a single table can also be added to another table, to have 2 tables.
All right, well, we are very close to the end here. Unfortunately, we have just too many questions to answer live right now. So I think we're going to have to put a stop to the question and answer right now. I apologize if we did not answer your question, but please feel free to contact us or Zulfikri to get more information. We'd be happy to speak to you about any of your engineering needs. Paul, would you like to say anything?
If Zulfikri can send us the questions, and then we have the emails of everybody, we can write a little memorandum with the other questions, and we can provide in writing answers to those questions.
Yeah, I will write it and summarize everything and send to all of people. Okay, thank you for your time, Paul. I would like to send greeting to the far maybe the far long way from Jakarta participant from Papua, Mr. Saul Ronsembre. Pak Saul dari PUPR di Papua. Terima kasih dari teman-teman di seluruh Indonesia yang telah bergabung dari Papua, juga dari Aceh juga. Ini adalah webinar kita yang ketiga. Mudah-mudahan kita bisa terus lanjutkan di bulan ke depan. Dan seperti tadi yang disampaikan oleh Paul dan Boas, bahwasanya pertanyaan-pertanyaan ini kita akan jawab. Dan kalau ada pertanyaan, silakan kontak saya, bisa lewat WA, karena saya selalu WA Bapak Ibu semuanya. Nanti kalau ada yang butuh detail, kebetulan Engineering Testindo lagi kurang sehat, Pak Haitam Sungkar, jadi tidak bisa join. Kita akan bisa datang ke tempat Bapak Ibu atau kita buat sesi khusus jika ada kebutuhan detail atau detail tentang riset yang ingin didiskusikan. Kita juga bisa mensupport di lain kesempatan. Burung dara cendrawasih, cari dulu di Papua. Cukup sekian, terima kasih. Semoga bermanfaat untuk semua. Terima kasih. Thank you very much for you, Paul and Boas, and for all participants. Terima kasih banyak semuanya.
Thank you also.
Thank you everyone for your time. We appreciate you coming to listen to us today. We look forward to hearing from you all again.